So I will open class with entertaining any questions. I'm always going to entertain. Any questions on homework? Yes. Which one? 18. Did I hear what else? 17. So that should take an hour of class. Let me look at these and see which one looks like the most fun. Okay, so let's take a vote. How many of you actually made an honest attempt at your homework? No, click in here. $17, $18, and $27. I'll tell you what. I did 17 in my office hours, right, last time. This group has it, right? If you're willing to talk to them, maybe you can share. You don't look too enthused about that. I can't do all three. That's the thing. We don't have enough time. You'll have to work that out. Does that sound okay to you? That's okay? It might encourage you to get to know each other a little bit. Number 18, I don't mind doing that one so much because that's an even problem, and the solution manual doesn't even have that. So a baseball diamond is a square with side 90 feet. Okay, so 33% of you did not do your homework. It's not a good thing. Okay, we have a test in a week, so you don't want to wait on these related rate problems because they are difficult. All right, so we have a baseball diamond and has 90-foot sides. A batter hits the ball and runs toward first base with a speed derivative of 24 feet per second. So I've got the batter, let's say they start from here, they're running this direction to first base. I'm assuming everyone knows that a baseball diamond, first, second, third, home. The speed here is 24 feet per second. Notice I put an arrow there to represent motion, right? It's not the length of a side or anything. It's just showing that that's what the direction the runner's going. Part A, at what rate is the distance from at what rate is his distance from second base decreasing when he is halfway to first base? That's part A. So I'm going to draw another one which will represent my moment in time. This is my general picture. This is my moment. And when he's halfway, he'll be right here. And this distance here will be what? $45 feet? Because he's halfway. And we are interested in the distance, the rate at which the distance between him and second base is decreasing. So second base is at the top. Connect that like this, right? Since I'm going to do that, I'm going to do it on the other picture also. On the general picture, I should label this, give it a letter, H, that's fine. Over here, I'll label it H, but you tell me, can I actually figure out what H is if I know this is 45? Yes, I should be able to because everything's fixed in time. So I should be able to determine what that H is. Okay, let's write down what I'm given, what I want. I'm given something, I want something. What am I given? In terms of the speeds, derivatives, the speed of the runner, right? So the rate at which this is changing. I haven't labeled this with a variable yet. So maybe I should call the distance from him to his spot on that line to first base, call it something like x. So I'm given dx dt. And that's what, 24 feet per second. So far, are we okay? All right, I want to know dh dt at exactly what moment? When x is 45, right? So this is moving. As x changes, h changes. Here's the moment in time. I believe that's all I need. Questions? I need an equation now. I need to relate h to x. So how would you like to relate h to x? Those look like diamonds, but they're squares, aren't they? That's a square, so just keep in mind this is a right. Boy, does it look like a right angle? It doesn't. On my screen, it looks like a really good right angle. On up here, it's the aspect ratio is a little different on the projector than on my screen. So, yes. At the moment in time, it is. But our equation needs to come from our general picture. It cannot come from the moment in time. So, any equation you can come up with that relates x and h together. Pythagorean on what? On the triangle? Which one? Which triangle? I guess the only triangle I have drawn there, right? This one? Are you saying on that one right there? Yeah? Okay, so I know one of the sides is 90. I know one of the sides is h. I don't know this side, except for the fact that if from here to here is x, from here to here is 24, then from here to here, what's left over should be what? 24 minus x. Right? I mean 90 minus x, sorry, 90 minus x. Right? Here to here is 90. This is 90 minus x. So this is 90 minus x right there, from here to here. And now I can set up the Pythagorean identity. Pythagorean identity says that the 90 minus x squared plus the 90 squared should be equal to the hypotenuse h squared. And that's all we require, right, is an equation relating the two variables together. At that point, if you're happy with it, differentiate it with respect to time. I think I'm happy with it. Are you happy with it? So here we go. All right, so I take derivative of this. I'm going to have to use chain rule here. 2 is going to come out in front. 90 minus x to the first power. Now I take derivative of what's inside. Derivative of 90, 0, minus the derivative of x, dx dt. So I'm going to put in here parentheses, negative dx dt. I don't like that 1 up there. I'm getting rid of it. Is everyone clear that this is the derivative right here of this part? Plus, what's derivative of 90 squared? 0, because it's a constant, equals the derivative of the right side, 2h dh dt. I'm always looking to make sure that dx dt and dh dt appear, right? They do appear, because they were up here. That's what I needed. They're in there. let's go through the things. Do we know what x is at the moment in time now? Yes, 45. Do we know dx dt? Yes. Do we know what h is? Not directly, but we said we could find it at the moment in time. So I am going to put a check here, but I'll just highlight it. We're going to have to go get that. And then dh dt is what I'm trying to figure out. So that's good too. So let's find h. So I can find h actually right here using this equation because I know what x is at the moment in time. So I can go here, replace x with what? 45. So this becomes 45 squared plus 90 squared equals h squared. And you break out your calculator. I don't think I have mine with me. I'll use my phone. So square root of 8100. Oh wait, is that right? No. Square root of 10,125. Square root of 10,125 equals h. And I'll leave it like that unless it's a perfect square. No, it's not. So I'll just leave it like that. And now I plug everything in. We should be there. So 2 times 90 minus x was 90 minus 45, so 45. dx dt, negative dx dt is negative 24 equals 2 times h, which was the square root of 101.25, and then times dh dt. Questions? Canceling 2's here. What's 45 times 24? Negative 1080. And then on the right side, I have that square root, so I'll divide through by the square root. I think I'll actually do this now. Divided by, I'm getting negative 10.73 is approximately equal to dh dt. And what would be the unit of measurement on that? Feet per second. Does that clarify at all any question that you had? Yes? Okay. Part B says, at what rate is his distance from third base increasing at the same moment in time? So they want the same exact thing to be done, except that instead of having h go from here to here, h is going to go from here to here, right? Do I need to do that one, or you think you can do that one? Okay. Yeah. All right. That might actually work out to be easier, because if I'm drawing it this way and calling that h, then my Pythagorean on this triangle is a lot easier because it doesn't have 90 minus x. It has just x on this side, right? So that might be a little cleaner. Okay. All right. That was number 18. I'm also being asked about number 27. Is that right, 27? Someone asked about 27? Yes? Okay. Gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. So have you ever seen those conveyor belts that they have hooked up to a truck? There's my truck. And they have dirt, and it dumps it? Yeah. Okay. Yeah. So it says that this is being pumped in 30 cubic feet per minute. If you've ever been to like one of those landscape material places where they have like mulch and different things like rock and gravel, they usually have big conveyor belts, and that's how they make those big piles. The trucks will dump it onto the belt will take it way up, it'll dump it, and it'll form a cone. So, okay, so it's being dumped in at that shape, into the shape of a cone whose base diameter and height are always equal. So I have a cone, this pile is forming a cone, and it's saying that the base diameter, which I will call capital D, and the height, H, are always the same. So it just happens to turn out that with this particular material, rock or pebble, whatever it is, as the pile grows, the diameter is always equal to the height. Just the way it's working out for this particular material. How fast is the height of the pile increasing when the pile is 10 feet high? How fast is the height of the pile increasing when the pile is 10 feet high? So I think that's enough for me to have two pictures. I have a general picture and a moment picture. So here's my general. Here's my moment. In the general picture, I have my cone. I know the height is h, and I know the diameter is also h. So I'm just going to put h here also. And that pile's growing, right? It's moving, right? But at the particular moment in time that I'm interested in, my height's what? 10 feet. But that means also the base of the cone is also 10 feet. What is given to me? And what do I want? So what's given? $30 cubic feet per minute. Cubic foot is a measurement of volume, isn't it? So this is the rate at which the volume is changing. So dV dt, change in volume with respect to time, is this. So I'm given that the dV dt is 30 feet per minute. What I want to know is what? How quickly the height is changing, dH dt, at exactly the moment when what? When h is 10. Good. And that should be enough. I need to connect the volume of a cone to the height of a cone. So let's go look at our formulas and see what the formula we have for cones are. We have the volume is 1/3 pi r squared h, right? But I need my equation to have just h's in it, or v's and h's. And the good news is that I know that the diameter is h, right? Diameter for us is h. But the diameter is twice the radius, which means the radius is half the height. You could have said that from the beginning, right? If the diameter is h, then the radius is half of that. So what I'll do is I'll rewrite this equation. I will replace my r with 1/2 h. I need to square that and then multiply by h. Are we all good? What is 1/2 h squared? 1/4 h squared? And that 1/4 that we're going to get, I'm going to move it out front and multiply times 1/3. That'll give me 1/12. So I'm going to have volume is 1/12 pi h what? squared times h, which would be h cubed. We still good? That's what I want to differentiate. We plugged in the actual value before the derivative. Yes, because what you're doing then is you're stopping everything from moving and then asking the question, how fast is it moving? Yeah, that's exactly right. So the replacement always happens after the differentiation. And you would have seen, if you would have replaced it with 5 here and then place that with 10, then when you take a derivative, everything will be a constant, and derivative of a constant is 0. So you'll get 0, which won't make a lot of sense. All right, so here comes derivative. dv dt is the left. 1/12 pi is a constant times the derivative of h cubed. 3h squared, chain rule, dh dt. And I believe everything we're good with. dv dt we have, h we have, dh dt is what we want. So dv dt was 30 equals, I'm going to put that 3 over the 12, make that a 1/4 pi. And then h squared is 100, 10 times 10, and then dh dt. 100 divided by 4 is 25. So this is really 25 pi. And I'll divide both sides by 25 pi. So 30 over 25 pi is equal to your dh dt. What's that measured in? Feet per minute. Now, did the back of the book have a decimal, or did they leave it like that? They reduced it to 6 over 5 pi, which, yeah, okay. This is 6 over 5, but questions? A lot easier when I show you, right? All right, well, if we have time towards the end, we can revisit maybe number 17. Let me just try and get through what I need to get through today. Review for the exam, I'm working on it still. My plan is to send it out tomorrow via email, so you have something to work on over the weekend, if you'd like. But remember, homework is always the first thing you need to do, you know, before you start to go to the review. All right, so try and get all that out of the way first. All right, so the good news is we're going to move away from word problems. All right, it's good news. We're going to head into chapter 3. And chapter 3 is titled, well, it's titled Inverse Functions. But what we're really interested in right now are the exponential and logarithmic functions. So what I'm going to do today is 3.1, 3.2, and 3.3 all kind of together mixed up into one lecture. I don't really care for the exact order of what the book does, and I don't really care for some of the detail they show. Exponential and logarithmic functions are 2 functions that came from college algebra. So this is stuff you've seen. 3.3 is where it's new, where we talk about the derivatives of those. So I'm going to spend first a little bit of time reminding you what the exponential functions are, what they look like, how they behave. Then the logarithmic functions will do the same thing. Then we'll look at derivatives. So what about exponential functions? An exponential function is any function that looks like this. It is any function of x, so x is the variable. Your base, a here, is a number, and that number has to be bigger than 0, and it cannot be 1. So some examples of exponential functions are something like f of x is 2 to the x. That's an example of an exponential function. We call this the exponential function base 2, because the base is 2. And any exponential function that you can think of that has a base, as long as it's a positive number, not 1, it qualifies. So 1/3 to the x would also be an exponential function. Why do you think we throw out 1 as a possible base? 1 to any power is 1. So it would just be a flat line that's not very interesting. So we want them to do something other than just be flat. So that's why we have that requirement. And then the reason why we make it sure it's positive is because we know that when you raise negative numbers to powers, it changes the sign sometimes. And what you get is something that you cannot draw. It's not continuous. You can't draw it without picking up your pencil. So we just throw that out completely. All right, so what do these look like graphically? Okay, what do exponential functions look like? We really have two scenarios. You can have a graph that looks like this, or a graph that looks like this. These should always cross through the point 0, 1. Why is that? Take this, plug in 0. What does it spit out? 1. Right? Anything to the 0 is 1. So no matter what I choose my A to be, if I plug in 0, I should get 1. So I should always have a y-intercept of 0, 1. Now this over here, this graph has what we call a horizontal asymptote towards the left. So that means that the limit as x goes to negative infinity of this particular function is what? 0. So as I head to as I head to negative infinity, the function is getting closer to 0. What about if I head to positive infinity? Where's it headed? Positive infinity. So as you go to the right, it goes up. This right here is referred to as exponential growth. That's one of those things that's used like way too much by newscasters. I hear it all the time when I'm watching it. The crime rate's growing exponentially. They love to throw that out there, right? Exponential growth is pretty, I think the common person just means like really fast, right? It's growing exponential means it grows really quickly. So when do we get this case versus this case? What dictates which of these two it's going to be? That A, right, that base? It'll be exponential growth when A is greater than 1. So if your base is a number that's bigger than 1, you're going to grow exponentially. Over here, we don't call this exponential growth, we call it exponential decay. And then this happens when? When A is between 0 and 1. Tell me about the limits here on this one on the right. What's the limit as x goes to negative infinity? Positive infinity this time. What's the limit as x goes to positive infinity? 0. So it's kind of like the opposite of what we just had, right? Any questions on the graphs of exponential functions? Basic idea. So from now on, if we're like, hey, we're looking at this function we've got, it's like 5 to the x, 5 raised to the x. We should all know it's going to go up forever on the left. To the right, it's going to go to 0. Yes? All right, so let me ask you a question. What is the limit as x goes to negative infinity of 4 to the x? 0? Infinity? 0, right? Why is that happening? Because we know 4 to the x looks like this, right? That's what this looks like. So as I go to negative infinity, it's headed towards 0. Do y'all follow that? Okay, so let's try something a little different. What about this? What's the limit as x goes to negative infinity of 4 to the negative x? 0 or infinity? So without looking at a graph, because see, what's different about this graph is that in our formula, a to the x, we didn't have a negative x up there, right? So there's multiple ways to approach this. Here's the first way I want you to look at it. If I take a negative number and I plug it in here, then it's going to be a negative and a negative, which is going to be a positive number, isn't it? So isn't this really the same as letting x go to negative infinity? Plugging it in here is really letting that exponent become positive infinity. Negative, negative is positive. So you're really looking at this function again, but this time going out to the right. So it would go to positive infinity. That's one approach. Another approach would be to just do this. Rewrite it first as that, right? 4 to the negative x is the same as 1 over 4 to the x. And now let x go to negative infinity. Where does 4 to the x go when you let x go to negative infinity? We just said 0, didn't we? What's 1 divided by a number that's getting smaller? It's going to get bigger, right? It's going to become infinite. So that's another approach. Another approach is to just go one more step and rewrite 1 over 4 to the x as 1/4 to the x. Are these two the same? You put the x on the 1. What's 1 to any power? 1. And then you put the x on the 4 and you get 4 to the x. So this and this are the same. Now, this exponential function, what's your base? 1/4, which is smaller than 1. So the picture of this one looks like this, doesn't it? That's what that looks like. And I'm going to negative infinity, which means that I'm going up to infinity. So no matter how you do it up here, you need to be able to understand the behavior of these things in different points of view. What's wrong with y'all today? Are you okay? Y'all seem like really zoned out. You want to do more word problems? Is that what it is? You missed the word problems. All right, I understand. All right. So what is that one very special exponential function that we have? There's a real special one. The natural exponential function. Now I'm allowed to choose my base however I want, right? As long as it's bigger than 0, not 1. So if we choose our base to be this number e, then that is an exponential function, right? A is e. E is approximately 2.718, blah, 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 irrational number, right? Non-repeating, non-terminating decimal. But if that's my base, this function is called the natural exponential function. So it's a special case of a general exponential function. Most people would say there's nothing special about it, right? Because, you know, you could have a 2 there, you could have 4 there, you could, shoot, I could have f of x equals pi to the x, right? Who cares? What makes this one so special? Why do we call it the natural exponential function? What's that? It actually, the way we figured out that this was a special one was that we were actually looking for a function that had a certain property. Okay, we needed a function to have a certain property for a lot of things to work out for us. And this function is the only function that has the properties that we wanted. It's unique. There's no other one that behaves like this one. So let me explain to you what the property is that makes this one so special, right? The first property of this very nice function is that when you plug in 0, you get 1. So we really would like, we were looking for a function. We said we really need a function that when you plug in 0, you get 1, right? And then the next property that we really needed to happen was that we needed the derivative of that function to be equal to itself. That's what we were going for. Is there a function out there that when you plug in 0, you get 1, and then when you take its derivative, it is exactly the same function? And we looked, and we actually were able to determine this is the only one that behaves that way. So this right here is the most important property. The reason this property is important is because, look, if I define a function over here, f of x equals 0, okay? That's the constant flat line, like kind of this class looks like that right now. If I'm taking like a view of your demeanor, it looks kind of flat line right now. Still, it's dropping negative now. Okay, if you just take a constant function, right? What's the derivative of this function? 0, so it's itself, right? But this is what we would consider to be a trivial result. This function does nothing, right? It's boring. You plug in something to it, it spits out 0. It's flat. Derivative of that is 0. So who cares? So this is a trivial result. That's why this property is so important. If you plug in 0, I don't want 0 to come out, I want 1 to come out. This doesn't behave that way. So let's talk about this second property, though. What does it mean to say that it is its own derivative? Well, we know that e to the x looks like this. Why do I know it? Why do I know it looks like that and not the other way? Because e is 2.718, right? So it's bigger than 1. So I know it's exponential growth. If I were to come in here and I say, hey, everybody, what is the slope of the tangent line at 1? That means you go up to the function, right? And you're trying to find the slope of this line. Well, guess what the slope of that line is? It's the height of the function there. See, that's what this means. The slope of the line at x, the slope of the line at 1, is equal to the function's value at 1. So it's just equal to how high it is off the ground. So the pitch of that line is equivalent to the height. Does that make sense? So what is the slope of the line there? E to the 1. Right? The function is e to the x, so this is e to the 1. What's the slope of the tangent line at 2? E squared. What's the slope of the tangent line at 3? E cubed. What's the slope of the tangent line at 0? 1. Because That's the function's value at 0. So there is only one function that exists out there where if you want to find the slope of the tangent line, all you have to do is look at the actual y-coordinate of the function there. That's the only one that does it. It is unique. I can contrast that with something like the parabola x squared. What's the derivative of this? 2x? Okay, so go out to 1. Go up here. What's the slope of the tangent line here? What's the slope of the tangent line here? 2, because you're plugging 1 in here, right? The slope right there is 2. But how high are you off the ground? 1. See, they're not the same. That slope doesn't match the height. And no function that you can ever give me will ever do that except e to the x. It's the only one. Y'all don't look excited about that, but that was pretty major thing. That's why it's called the natural exponential function. It naturally occurs to be the only one that behaves that way. All right. So that leads us now to start talking a little bit about derivatives of these things. But before we do derivatives, let's talk about logarithms. So what is a logarithm? What's a logarithmic function? So start a new page. So if we define a function f of x, and then we write this log, then a little subscript ax, this is called the log function base a. And we have some restrictions on a again. Same restrictions we had with exponential. A has to be positive, a can't be 1. Now, what do log functions look like when we graph them? Well, we have two basic scenarios again. We have this, and then we have this. We'll have this one on the left if a is bigger than 1. We'll have this one on the right if a is between 0 and 1. So very much like the exponential, there's two cases. One when a is bigger than 1, one when a is smaller than 1. You could call that logarithmic growth and logarithmic decay if you wanted to. But there's some more subtle things that are happening that we need to be aware of. With exponential functions, we didn't talk about this. I should have. So I think I'm going to go back. We didn't talk about domains. What's the domain of an exponential function? All real numbers, right? What's the range of an exponential function? 0 to infinity, but not including 0, right? So I'm going to write that down here. I think I'll put it right below here. The domain of an exponential function is all real numbers, so negative infinity to infinity. The range of an exponential function is 0 to infinity, meaning the y values have to be above 0, so positive, right? It's the only thing that can come out of an exponential function. We clear? Now back to the the logarithmic ones. Tell me a little bit about the domain of the logs. 0 to infinity. And what about the range? All real numbers. It's the opposite. Exactly the opposite. of what we just had for exponential, isn't it? Domain 0 to infinity. The graph only exists to the right of 0. Only to the right of 0. The range, everything that comes out, up and down, it goes forever in each direction. On this log function on the left, what's the limit as x goes to infinity? So as you start moving out to the right, keep going to the right, where's the function headed? Infinity. It's kind of slow. It's much slower than exponential functions, but it is eventually getting bigger and bigger and bigger as you go. So it would be infinity. Does it make sense for me to try and ask you now the limit as x goes to negative infinity? I can't because I can't go past 0. So how about the limit as x approaches 0? From the right. Can I do that? Okay, where's this function headed as I go to 0 from the right? Negative infinity. These are just like fundamental characteristics of exponential and log functions that we just need to be familiar with as we move ahead. That way we're like, okay, yeah, you've got a log function, we're approaching 0 from the right. Obviously that's going to negative infinity, right? From this. All right, what about this one over here? This is a little bit different. What's the limit as x goes to positive infinity? Where's this function headed? This time it's headed to negative infinity because it's going down forever. What's the limit as x approaches 0 from the right here? Positive infinity. So as I come in from the right, it's going to go up. Is everybody just getting ready for March Madness? You're just nice and calm and sedated today? Just ready to get all excited? Man. Have I told you about my cartwheels? No? I've always wished I could do a cartwheel. I can't do a cartwheel. If I could ever do a cartwheel, then I would do a cartwheel in class. Because I would just want to see the look on everyone's faces. If I just do a couple of cartwheels across the class. No, I don't want to try. I don't want to try. I've tried too many times in my life. I gave up about 15 years ago. And just as a way to get everyone kind of woken up. You know, it's like, what the hell, he's doing cartwheels? Yes, I can do a backflip, but I can't. No, I can't do it. I'm just kidding. I can't do a backflip. I'm gonna break my neck up here. All right. So basic idea of log functions, right? They're all dictated by this a, just like the exponential function was dictated by the a. But there's a more important connection between exponential and log functions from college algebra that hopefully was stressed to you. And I think we alluded to it when we were talking about the domain and range were flipped here, right? They're exactly opposite. That's because exponential functions and log functions are inverse functions. They undo each other, right? An inverse function undoes another function. So like you have a cosine function, you have the arc cosine undoes it, right? You have a square function, squaring function, you have a square root undoes it. Same thing here. If you have an exponential function, a log function undoes it. If you have a log function and an exponential function undoes it. So that is why if you were to take f of x is equal to a to the x, with a being greater than 1, and you take another function, g of x, and let that be log base a of x with a greater than 1. So using the same a, if I graph both of these together on the same axes, the exponential function would look like this, right? Because a is greater than 1, it's exponential growth. The logarithmic function would look like this. And what makes functions inverses geometrically is if they are reflections of each other over the identity, over the diagonal. So if you take the diagonal and you reflect them over, that's what an inverse is. It switches your x and y coordinates. So if you take like this coordinate right here is the coordinate, what, 0, 1? If I flip that coordinate over and make it 1, 0, right? That should live on the other function. And it does, doesn't it? And that works for every single point on this graph. So just the moral of the story is remembering that these two functions are inverses. All right, next thing. The special log function. What's the very special one? There's actually two that are used a lot, but I'm going to mention just the one that we really like, the natural log. The natural logarithm. I'll just say natural log function. So what is the natural log function? It's the function, it's a log function with its base being what? 10 is not the natural log, e. It's the base e log function. Now, why is the base e so important? Well, I already tried to explain to you why e to the x was important, right? It's its only derivative. So, of course, its inverse function is going to be important too. And that's what makes this one so important, is how it's connected to the other one. But we do not like to write it that way, right? What do we write instead? ln x. And we don't write the subscript anymore. It's just understood that when you write ln x, that you really mean the log function with the base being e. And you have to know that. I've always felt like this is kind of a shortcoming in mathematics because I would just prefer we just wrote it this way all the time so that you know that the base is e. Using this shorthand, students lose sight of the fact that the base of the log function is e. That it's it's a special log function, but log base 2 is another log base 7 is another log base e is another, but it's a special one. So why is it that we gave it a special notation? And there's a story behind this. It has to do with typewriters and the fact that the natural log appears so many times within technical writing, technical journals, that back before even computers, if you had to type a research paper and you had to write the log function maybe 200, 300 times, subscripting on a typewriter sucks if you've ever done it. Anyone here ever used a typewriter? You don't have to date yourself here, but I mean, okay, I've used them. I mean, you type, and then when you want to subscript, you have to like do a rotation of the drum, and then you go back, and it slows you down. So instead of doing that, you just do natural log x. You just keep typing away without having to stop, right? So it was meant to help. It actually, I think, kind of messes people up a little bit with forgetting what it really means. Now, I mean, word processor still sucks to subscript, right? Unless you're doing like LaTeX or something where a technical math writing language. Okay, so the natural log function. That one obviously looks like this. Right? It's this kind of function because the base is bigger than 1, right? So we all know that as you go to infinity, the natural log function goes to infinity. As you approach 0 from the left, it dives down to negative infinity. Got to remember that. Okay. The other special one, which don't even write this down, the other special one is the base 10 log function. And whenever we use base 10, we don't write the 10. Instead, we just write log. So if you write log without anything, it's base 10. If you write ln, it's base e. And the reason why the shorthand there, same thing as up there. Typing that, log x, is much easier to type. And why is base 10 so important? Our number system is base 10, right? 10 fingers. That's where it all came from, right? So 10 was an important log, so we give it a special notation. All right. What were some things with logs that we need to remember? Because there was a lot of stuff with logs. How about some of the properties of logs? How about this one? There's a lot of properties, right? So let me just start listing some things. How about this? What is a log of any base of 1? So I don't care what the base is. If you try and plug 1 into a log, what comes out? 0? Yes? And you could tell by the graph. Remember I said it had 1 0 in it? Now, next to this, I'm going to write down for our special case. Look, this is our special log, right? Natural log. If I try and plug 1 into any log, I get 0. So, of course, if I try and plug 1 into the natural log, I should get 0. This is ln, by the way. ln, not in. And I believe it's French. The French would say it not natural log. They'd say it like log naturel or something like that. They would go backwards with it. So, just FYI. All right, 2, what's another property? What is log base A of A? 1. So tell me what my special property would be that corresponds to this. Natural log of E is 1. The natural log of E is 1. Another property of logs. Log base A of A, oh, not A, that's an X, of A raised to the X is X. Now this is happening because of that whole inverse property thing I was talking about. A to the X is an exponential function, right? A to the X? That right there is an exponential function. If I plug the exponential function, a to the X, into the log function that has the same base, they wipe each other out and the X falls out. That's what's happening there. Now what's the special case? That would be natural log e to the X would be equal to X. More properties. If I have log base A of X times Y, I can rewrite this as log base AX plus, log base AY. We called this expanding a log, or like moving from left to right, that's expansion. Going from right to left, we call condensing. So this was a really important property of logs. Multiplication inside of a single log turns into addition of 2 separate logs. And there was another property for division, wasn't there? Subtraction. And these, I could have the blue ones over here, right? Do you want me to write them? I forget. Y'all don't like to answer. X, Y, natural log X plus natural log Y. This one would be natural log X over Y equals natural log X minus natural log Y. So those would be the special cases of these rules, properties. One more. And it's a biggie, but I need to go to a different page. We got this? Yep. Oh, what am I on? 7? 6? 6. Log base A of X to the N. So notice that this base is not the same as the base of the log. So if I have log base A of X to a power, This turns, anyone remember what this is? The n comes out front, n times log base a of x. So the property here is that that power can be pulled out in front of the log. That is going to be super, super useful to us. Why does this property work? Kind of weird. You could kind of convince yourself of it. Log base a of x to the n is the same as x times x times x times x, right? Yeah, the multiplication, right? When we said x times y, we said it split into two logs. So this would split into two logs. Each time we have a multiplication, it would split into a separate log. So you'd have log base ax plus another log base ax plus another log base ax, and you would keep on having those. How many of them would you have? N of them. So if you add n things together, you have n of them. So that becomes n of those logs. Now, you have to believe that you can split it into two in order to convince yourself, but if you're okay with that, then that's why it works. Okay, we ready? We got all the preliminary stuff out of the way? You ready to talk about derivatives? So excited. Derivatives. Derivative of exponential functions. So we're in 3.3 now in the book, okay? 3.1 and 3.2 are kind of a review of exponential and log functions. 3.3 is where we do calculus now. So I would like to know what the derivative of an exponential function is. So I'm going to give you the definition, and then from here on out, you can use it. And it's in your formulas, all right, on your sheet. Can I see it real quick? I want to see how the notation they use. It's formula 10. All right, so let's say we have a function, f of x equals a to the x. That is an exponential function, right? The derivative of this is itself times natural log of the base. Here's another notation of the same thing. If I want to take the derivative of a to the u, it's going to be a to the u itself times natural log of a. Let's do an example. Let's say y is equal to 4 to the x. What's y prime? Four to the x times the natural log of 4. The natural log of 4 is a constant, isn't it? So this is just like a number. So it's like the derivative of 4 to the x is almost itself, right? Almost, except we have to scale it by something. So remember I was saying slope of tangent line was equal to the function's value there? This one is almost what we want. Let's see why it works for e to the x, though. If this is e to the x, what's its derivative? E to the x times natural log of e. But what's natural log of e? 1. Right? Natural log of e is 1, which is why you get e to the x. Now, I'm not proving that. I'm not proving this, okay? Why this is true? You just have to take this on faith for now. How about this? What you need to see here is that. That's 4 raised to the remote, right? What's the derivative of 4 to the remote? 4 to the remote times natural log of 4 times chain rule. Okay, so think about it. You have, first of all, the derivative of 4 to something is itself. Then you always have that little natural log 4 that pops out, right? I've taken the derivative of 4 to something. But that something up here needs to be taken care of with chain rule. So it's kind of like an outer function is the 4 to the something. The inner function is that sign. So I need to tack on to the end of this what? Derivative of sine, which is cosine x. Do you all see it? Let's do another one. E to the x squared plus 1. What is the, oh, sorry, that's y. I want y prime next to it. All right, so what is the derivative of e to anything? The exact same thing, right? E to that anything. Do I need to really write down natural log of e now? No, because it's always going to be a 1, right? So you don't need to write it. But then I still need to do chain rule. So times what over here? Derivative of what's up there? 2x. Yes, you can move the 2x in front of this. In fact, you would probably see it like that in a book. Right, that would be your derivative. Any questions? I think that's sufficient. I think I can move on. I mean, that opens up to a whole new can of worms, doesn't it? I mean, you can have like, you know, what's derivative of x e to the x? So now you'd have to do product rule, right? Or it could appear somewhere else. So just keep that in mind. Logs, you ready to talk about derivative of log? So let's say we start out with f of x equals log base a of x. The derivative of this will be 1 over x natural log a. That's also in your formulas. 1 over x natural log a. So let me show you an example of this. We'll start with the natural log. The natural log, what's the base here? E? Okay, so what's the derivative of this? According to this formula, it should be 1 divided by x. X is the argument of the function, right? So it's just x here. 1 over x. Then what? Natural log of the base. But what's our base? E. So it's just going to be 1. So it's just going to be 1 over x, isn't it? So the derivative of the natural log of x is 1 over x. The derivative of natural log of x is 1 over x. That's one of those ones that you've got to have like hardwired. Kind of like if I say, what's the derivative of x squared? Everyone's like 2x. This should be the same thing now. try something else. Y equals log base 3 of x. What's the derivative here? So 1 over, right? Just follow the formula. 1 over x ln 3. That's it. Does that make sense? Just following the formula? What about this? What's the derivative of natural log of cosine x? So first of all, it's chain rule, right? The outer function is natural log, inside is cosine. So you start with the natural log. What is the derivative of natural log of my yellow cursor? 1 over my cursor, right? That's what this said right here. The derivative of natural log of x is just 1 over x. So it's just going to be 1 over my cursor, 1 over cosine x, yes? Am I done? No. Times, now chain rule, derivative of what's inside. Negative sine x. What's negative sine divided by cosine? Negative tangent of x. The derivative of the natural log of cosine x is negative tangent x. Oh, yeah, we're just building up right now. It'll be more similar to what you see in the homework. Yeah. This is just to get the basic concepts going. Okay, so you could start this out by saying you have composition, you have outer function natural log, next function in is what? Square root, next function in is x squared plus 1, right? And you could start and do your chain rule and go through it. But before I do that, I'm going to rewrite this like this. Do you agree that's the same thing? And then I'm going to use a property of logs, property 6, that says if I have the log of something to a power, what can I do with the power? Bring it out. And that just makes it a little bit easier to take the derivative of. That's all. It's going to save me some time. So let's do our derivative over here. The 1/2 in front is just a constant. I'm just going to bring it along. What is the derivative now of natural log of this thing? 1 over that thing, right? Am I done? No? Now I need derivative of what's in here, which is 2x. I believe these 2's cancel. So your answer is just x over x squared plus 1. You'll see that? Let's do a little more. If y is equal to the natural log of the square root of x plus 1 over x minus 2 squared times x plus 7. to the 5th power. And I want to take the derivative. Now I could look at that and I could say, okay, I've got natural log of something, right? So I can do 1 over that, and then I could say I'm going to go in there and I'm going to start doing what? Quotient rule, right? On this, enjoy yourself. That's going to suck, right? So let's use properties, okay? First of all, you have natural log of something divided by something, right? Division within a natural log, you can split that into 2 logs. So this will become, without taking a derivative, right? Natural log of square root of x plus 1 minus, right? Natural log of, and then everything down there, x minus 2 squared, x plus 7 to the 5th. So I've just used a property to split it into 2. Anything else you want to do? That's right. This right here is 2 things being multiplied. So I can split that log into 2. Just keep in mind you had a minus here. So these are going to split into 2 logs with a plus, but you have a minus in front of all of it. So that minus should distribute to both. While I'm doing that, on that first one, I'm going to rewrite the square root. Is that all right? Again, I'll highlight the fact that those are both negative. Comes from the fact that when you split this into 2 logs, there's a plus between them, but this negative will pass through to both, which makes them both negative. Do you want to do derivatives yet? No, one more property, right? The half can come out, the 2 can come out, the 5 can come out. Does anybody remember doing this in college algebra where you started with this and they said expand? This is why. All right? So the 1/2 comes out. -2 now comes out. 5 comes out. And now when we take the derivative, this is going to go much cleaner. Much, much cleaner. Remember what we would have had to have done. Quotient rule on this, which would have required product rule and chain rule and a bunch of mess. All we did is applied a couple of properties, and now we can do these one by one. So I ignore the 1/2, so here we go, derivative. I ignore the 1/2, bring it down. What's derivative of natural log of something? 1 over the something. Times the derivative of what was in there. What's the derivative of what's in there? What? 1. So I'm done. Next one. -2 times derivative of natural log of something. 1 over the something. Times the derivative of what's in here. 1 again. Minus 5 times derivative of natural log of something. 1 over something. Times the derivative of what's inside. 1. We're done. You could clean this up if you want. There's your derivative. It wouldn't look the same, I can promise you that, though. But you'd still be working on that probably for another 30 minutes. Easily. That would be not a fun problem to do a quotient rule on. Right? Derivative of the top would be a square root, so you have to do 1 over 2 root that, times the bottom, minus derivative of the bottom, but that's a product rule. But each one of those is a chain rule. See what I'm saying? It's a mess. All right, so I hope you see the value of that. Hang in there. We got 20 minutes. We're now going to do what's called logarithmic differentiation. And the best way to explain what it is to give you an example. So I've defined a function. I want us to find y prime. So when you look at this, you realize how nasty that derivative is going to be, right? Again, quotient rule. And so like in the previous problem, we were able to take this nasty thing and break it all apart. But what did we need in order for that to happen? We needed the log there, didn't we? And unfortunately, you don't have a log here, right? Agreed? So this is what this technique of logarithmic differentiation is all about. It's a way to handle a problem like this using something kind of tricky. What we're going to do is we're going to take this equation and we're going to take the natural log of both sides. And then we're going to take the derivative. All right, so let's try it. I'm going to bring in the natural log on the left side. I'm going to bring in the natural log on the right side. Now you're allowed to do this because the natural log function is a one-to-one function, meaning that taking natural log on both sides maintains the equality. You don't lose any information when you do it. It's beyond what I want to talk about now. It's something you should have maybe talked about in college algebra, one-to-one functions and the way they behave and their properties. But just know in this class, we can do this without messing anything up. It's going to be okay. And now we take derivative. But the left side's no longer y, is it? So we have to take the derivative on both sides of the equation implicitly. Implicit differentiation, which is kind of like what we were doing with related rates, except we're not going to do it with respect to time. We're doing it with respect to x. So what is the derivative of natural log of something on the left side? Derivative of natural log of something. 1 over that something, right? Yes? 1 over something times the derivative of what's inside. What is the derivative of what's inside? What's the derivative of y? dy dx, or y prime. I'm going to put y prime. Everyone follow that on the left side? Every time you use logarithmic differentiation, your left side's always going to look like that, 1 over y, y prime, because the left side's always going to be natural log y. Now the right side, we have to do a lot of work on. So before I come over here and get the right side's derivative, let's take a few moments to simplify this. So that means use the properties. Do you know what I mean by use the properties? I mean do all this that we did in the previous problem, right? Before we took derivative. I'm going to do that mentally. You would have what? Natural log, 3 natural log x plus 6 natural log x minus 5 minus 1/3 natural log x plus 1. So I'm not showing this work, but you would first do division, which would put these two in a log minus this in a log. Then you would split these into 2 with plus between them. And then you bring the 3 down, the 6 down, and this is a 1/3 power, you bring that down. You put it all together, do it on your own, you get this. And that's what we take the derivative of. So what is the derivative of this right side right here? So derivative of 3 natural log of x is, ignore the 3. It's derivative natural log of x. 1 over x. So 3 times 1 over x. Okay, plus the 6. Now what's the derivative of natural log of x minus 5? 1 over x minus 5. Anything else or no? Like derivative what's in here, right, which is 1. Okay. Then minus 1/3 times 1 over x plus 1. That's this last one. Let me clean it up. We're almost there. 3 over x plus 6 over x minus 5 minus 1 over 3x plus 3. Any questions? Go ahead. What? Yeah? We're not done yet. Yeah. Is that what you're saying? Yeah, because we're supposed to find out what y prime is, right? This is what 1 over y prime is. So what I need to do now is get rid of this 1 over y, so I multiply both sides by y. So y prime is equal to this right here, right? I'm cheating. That times y. But what is y? It's the original problem, isn't it? So what I'm going to do now is I'm going to replace y with the original y. Here's the original y, right? This right here. So I'm going to grab this. That's y. And I'm going to slap it right next to this. Or right on top of all that other shit. There we go. That's your answer. You don't need to clean that up. Does it make sense, though? So every time you do a logarithmic differentiation like this, your left side's always going to be 1 over y prime, which means you're always going to multiply both sides by y, which means you're always going to have your original y appear on this side, next to whatever this is. But I still would argue that this is much easier than you having to try and take the derivative of this using quotient rule and chain rule. It's still easier. I have 10 minutes, enough time to show you one last thing. All right, I know y'all look depleted. Are there any questions? Okay, in 10 minutes, let's see how you handle this. Real quick now. This is not a trick question. I want you to look at these two functions. What's the derivative here? What's y prime? (10x to the 9th), right? That's because your base was the variable and the exponent was 10. Over here, if I ask you what y prime is, what do you put? What is this here? This is exponential function, right? So this is 10 to the x ln 10. The difference, you see the difference between the two? It's all about where your variable appeared. Your variable's in the base, this is a power function. If your variable is in the exponent, it's an exponential function. The derivatives of those two things are completely different. One of the major mistakes I see students do is that for this one, they say that the derivative is x 10 to the x minus 1. That seems like a pretty normal mistake that I'd see, right? See what they did, right? Take the x out front, subtract 1. It's completely wrong. Cannot do it that way. That only works if this is a number and that's your variable. Okay, so no, no. So that leads me to this. If y is equal to x to the x, find y prime. What's the issue here? Do you see the issue? Your base is a variable, right? Which makes you think power rule, but your exponent's also a variable, right? So do you bring the x out and subtract 1? Or do you do natural log of x to the, you know what I'm saying? Like, not natural log. Do you do x to the x times natural log of x? Or is it neither one? What do you think? What do y'all think? Is that a power function? Is that like x to the 10th? Is it? No, because the exponent is changing, right? So it doesn't stay fixed. So it's not like that. Is it like this? 10 to the x. Well, that's the same, but the base is changing here. Here the base isn't changing. This is neither a power function nor an exponential function. It's something different, something we've never seen before, probably. So how do you find the derivative of that? If your variable appears both here and here? Well, more logarithmic differentiation. So what did we do in the last problem? We took the natural log of both sides. So what I'm going to do is I'm going to take natural log of y over here, natural log of x to the x. Now, on the right side, what can I do? Property of logs says that I can pull the power out front, doesn't it? So this turns into natural log y equals x natural log x. And now let me take the derivative. And I'm going to do it implicitly. What's the derivative of the left side? 1 over y prime. We said that's going to happen every time. On the right side, what's the derivative here? Product rule, right? That's a product rule. X times natural log x. So product rule said derivative of the first one times the second plus the derivative of the second one times the first one. So what's the derivative of the first one? 1 times natural log x plus, what is the derivative of natural log x? 1 over x times the first one, which is x. So 1 over y prime, or 1 over y prime equals natural log x plus 1. Right, 1 over x times x is 1. Am I done? Because I have to get rid of this 1 over y, so I multiply both sides by y. So you get natural log x plus 1 times y, which is finally natural log x plus 1 and times y, but y was x to the x. So the derivative of the natural log of, the derivative of x to the x is natural log of x plus 1 times x to the x. All right. Tell you what you should look at for homework. Page 168. Those are all just derivative problems. So that's roughly 20 derivatives using, they'll have chain rule and product rule and things built into them, but they're also going to have exponentials and logs in there now. And then 51 through 59, odd. Those are logarithmic differentiation problems, and it even says in the instructions, use logarithmic differentiation or an alternative method to figure out the derivatives. On a test, I will not tell you use logarithmic differentiation. Like, I wouldn't prompt you for that. So like on the problem that you had just here, I would not tell you use logarithmic differentiation. You would have to recognize that that's the only option you have. All right, so we're going to come back on Tuesday, and we're going to be awake. All right, no falling asleep. Fall asleep in class. It costs you 10 points on your next test. It says it in the syllabus, so you all need to wake up. Those of you who are falling asleep in here. I'm not sure there's anyone in here who can afford to fall asleep, so have a good week.